Well, good morning. This lecture is our final lecture and it's on multivariable decoupling by output feedback. And we're considering some linear state space equations, multivariable, given by the following state space and transfer function. And we can see in this now that we've got y1 as a function of g1 times u1 and g12 times u2. So it's a highly interactive multivariable process. And when we control multivariable systems, one of the issues is when you do a set point change in one variable, you get an effect in the other channels. And these effects in the other channels are called interactions. And in general, it's very difficult to control the interactions in a multivariable system, especially if you use a decentralized controller. So one of the options is to move to a centralized decoupling controller, which is what this lecture is about. So the idea now is that we're going to decouple the system, and what that means really is to reduce the interactions in the multivariable system, and we can do that using two methods. We can use a proportional control to affect initial decoupling, that's at the start of the transient response, and the integral controller to make sure that we get steady state decoupling. So that means the system actually tracks in the steady state and there's no crosstalk or interaction in the initial part or the final part. And the proportional integral controller is well positioned to help us achieve those two aims. If we look at generally multivariable systems, one of the things you've always got to consider in designing multivariable controllers, especially decoupling controllers, is where the poles and zeros are. So one of the things that's tricky about multivariable systems is that if we look at the original transfer function, it's not obvious where the zeros are. So we've got to use the determinant of GS is ZS over PS to get our zeros, and then the zeros to some extent dictate what sort of performance we can get out of the system here. If the system has got negative zeros, in general it is quite relatively straightforward to design a decoupling controller. If the multivariable system though has zeros in the right half plane, that's negative signs in here, then most form of decoupling control for multivariable systems of that type is very tricky. So just going back to our decentralized controller, the idea behind a decentralized controller is that one input controls one output, and we can have, this is a typical example of one of those, and here the controller is diagonal this way because we've got linkage between U1 and Y1, U2 and Y2. Now in a centralized controller, and notice here we have basically two controllers, two PID controllers. In a centralized controller for a 2x2, we're going to have four controllers now. So we've got sort of basic controls here, we've got an extra couple of controllers here. And so the controller structure now, rather than being a diagonal matrix, it's now a full matrix. And for this particular case, we'd have four numbers for the proportional controller, four numbers to the integral. So KP11 would be the proportional gain in there, KI11 would be the integral gain in there, KP12 would be the proportional controller there, and KI12 would be the integral controller there. Similarly, these would give you the same effects. That would be KP22 and KI22, and that would be KP21, KI21. So in this arrangement now, it's a matrix we're designing, and the implementation is done as four separate controllers. So there's much more difficulty now in choosing essentially, before we had say 4 parameters, now we've got 8 parameters to choose. So the design process has doubled in complexity, and it's not obvious at the first sight how to design these controllers. So we'll be looking now how to design the proportional controller and the integral controller to make our life a little bit easier in the design process. And one of the things that we're interested in is really, this is the system we've just seen, and this is a set point tracking characteristic. So we put a set point change on channel 1, so a set point here and nothing on this one. So this has got a set point change on, this one should be constant. And here's a set point change in channel 1, and here's the output 2. And this sort of effect is called the interaction. And this is an example of a centralized controller, and we've designed it to sort of make this interaction as small as we possibly can. This is the example of the same system controlled by a decentralized controller, and in these we tend to get more interaction. This is the interaction. This is a set point 1 tracking. This is the interaction on channel 2 due to the set point tracking. Similarly, if we swap the channels around the other way, they never behave in exactly the same way in both channels. Again, this is the interaction from the decentralized controller, and with the centralized controller we're hoping to reduce these interactions and then that gives us a better quality controller that we can do set point changes without too much interaction occurring. So let's look at the first part of the design. This is the proportional controller design, and this is used to achieve initial decoupling. So the controller is the form of U as K V minus Cx, where K would be a matrix full of parameters. We'd have to design now these parameters. If it's a 2x2, there'd be 4 parameters. If it's a 3x3, it'd be 9. If it's a 4x4, it'd be 16. So as the number of inputs and outputs grows, the controller complexity grows as a function of the number squared. So we need some sort of design methodology for this rather than just trial and error. So if we consider the state space equations, they're standard classical state space equations. This is the state space, this is the control law, these are the closed loop state space equations here, and we want to achieve certain set of properties to this now. We just want to achieve initial decoupling. So initial decoupling means that the variable you want to go off goes off in the right direction, and the other one more or less stays where it is. And that is true for every single channel in your multivariable system. So in order to look at this now, we've got to look at what's called the decoupling matrix. So for a multivariable system, it turns out there's a matrix called the decoupling matrix, and we can use this to help us in the design of that part of the control system. So if we consider the initial performance of a control system, we can say that x dot is ax plus bu. If we consider that x of naught is naught, then the x dot will be given by b times u. Then x double dot will be given by ax dot plus bu dot. So we differentiate this one to get this one. But x dot of naught is this term here, so which is that, plus bu of naught dot. Now in this term here, the bu of naught is the non-zero term. So we could get now potentially an a bu zero term coming here. X of naught will be naught, so these will be naught. U dot of naught will also be naught. So then if you went for the third differential term, that comes out as a squared bu of naught. So these red terms here are the x dot is bu naught, x double dot is a bu naught, and x triple dot is a squared bu naught. So this is a sort of structure now that we might be able to deploy. If we look at there's a structure for our differential terms. We could also look at the output now, yi. We could do this for each channel individually. So yi will be given by cxi. So therefore, yi dot will be given by c times a times x times c times b times u naught. So yi dot will be ci bu naught. Yi double dot will be the same as what we had before here, which is put a c in front of here. So it comes out as ci a bu naught, and this one comes out as ci a squared bu naught. So these terms here pick up a c when we look at the output initial conditions, and this has to be different for every channel. So this isn't the major C matrix, this is an individual row of the C matrix, and has to be done for each individual row individually. And if we do that, we compute this matrix here, this is the first row of the C matrix, this is the second, this is the third, down to the nth, and it's given by C1, because it's the first row, a to the d1b. This will be C2A to the D2B. Now these D parameters will depend now on when we compute these terms. This it could well be that CB is 0, so then we could compute CAB, and that could be 0, but eventually one of them will come out as non-zero. So the first non-zero term sets this number here. So let's say that was 0 and that was 0, and this one wasn't, then the D would be 2. Or say this was not 0, then the D would be 0. If this was 0 but this wasn't, then D would be 1. So that's how we can work out those things for the individual channels. And that gives us this matrix called E, which is called the decoupling matrix. And the decoupling matrix is an important matrix because if this matrix is singular, remember we talked about rank and the determinant being non-zero. One of the conditions for decoupling is that this matrix has to be non-singular. If this matrix is singular, it means that you can't decouple the system. So you could work out the rank of the system, and if the rank, say it was a 3x3 system, if the rank was 3, you'd know it's decouplable. If the rank was only 2, then you'd know you couldn't decouple it. Now we can apply the same thinking now to closed loop state space equations. Originally when we did the analysis here, this was for open loop state space equations. So if we apply the same analysis now to closed loop state space equations, we get a similar pattern appearing here, and what we get is that the differential term now comes out as because if we look at x dot, this is a minus bkc x naught plus bk. This is for the closed loop system. So if we set the initial conditions as naught, all the terms here become 0. The first non-zero term could be bkv, then the next one, when we do the analysis, comes out as a bkv, and the next one is a squared bkv. So we can see an emerging pattern here now, that these terms here are almost identical to the open loop terms, where these were a squared b, whereas the ones now are ab. There's an extra k comes in due to the controller. So we can get from this now that the decoupling matrix for the closed loop multivariable systems is given by E, which is the decoupling matrix for the open loop systems, times k, where k is the controller, proportional controller we're trying to design. So we can see now for initial decoupling, if you make this matrix, this overall term, diagonal, then it'll be decoupled because a diagonal matrix is decoupled. So that gives us an easy design equation for k then. K is simply e to the minus 1. So this gives us our first part of the design now of our proportional control system. And then what we do is we compute the decoupling matrix. We make sure it's a full rank. And if it is a full rank, we're able then to deploy that, the inverse of the decoupling matrix, as the controller structure for our proportional controller. So this is a first stage now in our design. So to achieve initial decoupling of the form of u with the controller u because kp v minus cx, well, that's a matrix there. We could choose kp as the decoupling matrix inverted times a set of diagonal gains. So we've got some tunability in it as well. So this is the first part of our design now, and it involves computing the decoupling matrix and using the decoupling matrix inverted as the structure for our proportional controller. Next thing we need to look at is steady state decoupling. So this is where we need an integral controller to achieve steady state decoupling. Remember, integral controllers reduce steady state error to 0. So we've got our proportional controller now, which we've designed for initial decoupling. Now we're going to design the ki to achieve steady state decoupling. So these now could be the state space equations of our classical multivariable PI controllers. You've got x dot is ax plus bu, z dot is v minus cx, and then these would then form the closed loop state space equations, just as we've achieved closed loop state space equations for other state space representations. This equally well works for multivariable. That's the beauty of state space. We can extend it from single input to single output, and it's exactly the same, which is like highly advantageous. So from this we can get the closed loop state space equations, and the closed loop stability is then come down to the eigenvalues of this matrix here. If the closed loop system is stable and we've got integral action in, then we're going to achieve steady state decoupling. So the main trick now is to design the Ki to ensure that this overall set of eigenvalues are stable. Now we can use our Scher's formula to simplify this blocked transfer function into two separate smaller transfer functions. So that gives us then that the determinant of Si minus A minus BKC, that's the proportional part of the controller, becomes part of the stability equation. So if the proportional control is stable, that's a necessary condition. Then we've got then the determinant of S in I into GS BKI. Also, the eigenvalues of this now have to be stable as well. Now, if we choose Ki equal to minus epsilon times Ki, where epsilon is a small number, then we can use singular perturbation analysis to re-represent this part of the equation as Si plus epsilon Ca to minus 1 bki plus epsilon squared into some term plus epsilon cubed into some term. And if epsilon is small, then epsilon squared is very small and epsilon cubed is even smaller, so we can disregard that part there. So the stability equation here simplifies down to this term here. And this was originally invented by a chap called Professor Brian Porter, who was actually a professor at Salford University, and believe it or not, he was my PhD supervisor. So anyway, that's a side story. So this part here now is stable, and we need to ensure now this part here is also stable to make sure the overall closed loop system is stable. This can be simplified down now if we choose a relatively small integral controller to determinant of Si minus epsilon Ca to minus 1 bki is stable. So we can see from this now that if we choose Ki equal to Ca to the minus 1b to the minus 1, that's a little bug in there. See if I can get my no, wrong bracket. So this is to the minus 1. I'll just have to put the fix in here so I can remember it. Let's go into here we go. So if we now choose Ki as Ca to the minus 1b to the minus 1, then when we multiply these two terms together, then this just becomes simply the unit matrix times epsilon. So you're guaranteed then that this is stable, because Si plus epsilon I is going to be stable, definitely. So this is the trick now that we can apply to ensure that this part of the expression is always stable. If we choose Ki equal to Ca to the minus 1b to the minus 1. Now we know that minus Ca to the minus 1b is actually G naught, so which is used in this relative gain range things. So if we choose Ki equal to G naught to the minus 1 times a little gain, then we will achieve stability in the closed loop system. We probably don't need that sign there either. So Ki is epsilon Ca to minus 1b, which is epsilon G naught to minus 1, and this gives us then the thinking behind designing the controller structure Ki. It's simply some gain times G0 to the minus 1. And this has come about through taking the system here and using Scher's formula on this to simplify this into a slightly smaller, convert a 2 by 2 into 2 sets of 1 by 1s, that which comes down to here, then ensuring that this part is stable and then ensuring this part is stable. So this is stable through the proportional controller and this part is stable through the integral controller, and by using some singular perturbation analysis we can analyze this to coming down to simply that Ki is G0 to the minus 1 times a small gain. And that gives us then the design for our two control systems. So for our PI controller now, to achieve decoupling, we're going to choose a proportional controller Kp equal to the initial decoupling matrix times the diagonal set of gains. I'm going to choose our integral controller as G0 to the minus 1. So that's another set of diagonal gains. And so it's the initial decoupling matrix and the final decoupling matrix of the open loop system that we use to design our proportional plus integral controller structures. And if we had a look at this now, here's a multivariable system which I've chosen. It's fairly interactive, and this is our centralized controller design, and we could now have a go at designing a controller for that. So the first thing we could do is take our transfer function, and it's got 4 separate poles in it. So we can have a pole at -5, pole at -11, pole at -31, and a pole at -1. And then we could use our Gilbert's algorithm to get the ABC. So this is the ABC now for this system here. Then once you've got the ABC, we can now compute some of the matrices. So the first thing we need to compute is the decoupling matrix, and we get that by the first one is C times B, then it would be C times A times B, CA squared B, until one of them is non-zero. But fortunately, in this particular case, C times B is non-zero, and therefore E is C times B. So E is C times B, and this is what C times B comes out as. If we then invert that matrix, that gives us the proportional controller structure here. So this is the decoupling matrix EB. That's C times B. This is CB here, where that's the C and that's the B. So we multiply this into this, we get this. Invert this then to get Kp, and that's our proportional control structure. The G0 is based on -C inverse of A times B, which is G0. So if we can work out G0 for this system again, going back to here, we know that C, A to the -1 times B minus it. We could compute that, and that comes out as 21 minus 0.661. And then if we invert that matrix, we get the Ki. So we've used the initial decoupling matrix E to get Kp, and used the steady state decoupling matrix open loop G0 to get Ki. Then we can put this, then goes into here, and this goes into here, and then this becomes now our multivariable controller to achieve decoupling. And we've got some tunable gains here on the loops. That's your proportional gain, integral gain on loop 1, proportional gain, integral gain on loop 2. So we can now implement this, and I've implemented this using a function block in MATLAB, and inside that function block I've implemented this equation. So this equation now can be implemented in this MATLAB function block, and so that's what I've done in here. So I define what Kp and Ki is, then I've U is, this is a matrix operation because E and Z are little vectors and Kp and Ki are matrices, and I've got some gains in here as well just to tune it. So this is the code now I would type inside the function block, and then E1 and Z1 and E2 and Z2 feed into the function block, and U1 and U2 come out. So it's an alternative strategy for implementing this structure here, which is I found it a little bit easier to code. And when we got our controller structure here, you could just essentially take this equation and pop it into this box. And when we apply that, this is the sort of performance we can get. So this is the centralized design step change on channel 1, and this is the interaction on channel 2, and this is the equivalent decentralized design. And if we swap channels, this is the set point change on channel 2, this interaction on channel 1, and this is the corresponding decentralized. So looking at these a little bit detail, we can see this has got something about like quite a big interaction here. This is significantly smaller here, and on this channel here again we've got quite a big interaction here, about 40%, whereas this is only in the sort of 5% interaction. If we have a look at this for real in MATLAB, here's my system now. So there's my little function block. If I click on this, you can see there's my KP code, there's my KI code, there's my controller equation. So got some other code in here that's just sets up the initial conditions, sets up the errors, and then outputs the different signals. So this has got a tunability in it, and I've actually slightly tuned it differently. I've put a 16 and an 8. Originally I had 6 and 6. I've now got 16 and 8 in there, but I can choose those numbers now. There's like tuning parameters. If I run the simulation now, just a quick check on what's going on. So we've got let's do a step change in channel 1 and no step change on channel 2. So step change now on channel 1. If we run this, then we can look at the performance. So this is the set point tracking performance. This is over 2 seconds, this, and you can see this is my interaction here. It's quite small. It's really sort of more or less decoupled the whole system. If I go swap channels, so make this 0 and make this one 1, I can do a step on the other channel now to see how that part's decoupling. So run this again. So this time again, this could be maybe tuned a bit more. We could get a little bit, get that to keep going like that and across there. But you can see the interaction here is really tiny, small interactions. It has really decoupled the system. If we compare this now to our corresponding decentralized design, this is the same system now controlled with 2 decentralized controllers. And if I've just set up a PID here because it's easy for me to set up a PID. So I've got gains of 1 and 5 in there, and I've got gains of 3 and 10 in here. So I've got significant gains in here. If I now come to run this, we can look at the performance. Let's just see what we're doing. If this is a step on channel 1, and here's a step on channel 1, so it's on the same sort of time scale, so it's similar sort of transient response. But you can see now the interaction is significantly larger. It's probably about 35% interaction, whereas before it was about 5%. So we're really getting rid of this interaction here using the centralized controller. If we change this one, put this as a 0 and put this as a 1, and again run it, these files will be available on Blackboard for you to load in and run. Run it again, so you can see this time we've got the same sort of performance as we had on that other channel, but this time we've really got a lot of interaction, got about 80% interaction. So that's a really massive interaction. You remember last time it was down in the like 1 or 2%. So if we compare this one now with our centralized design, that's a channel in this one, so it's the same channel. Look at this one. This is our centralized design. So you can see now the interaction is really quite tiny, and whereas before it's up to 80%. So the decoupling has really worked for us. And so this now is the potential that we've got in designing decoupling controllers, and inside this box now we implement the a proportional and integral controller, which are matrices as opposed to like just a diagonal matrix. So we've got 8 parameters in there, and these now are implementing, remember, our controller, which is given by this type of equation here. We work out the initial decoupling matrix, make a proportional controller that's equal to the inverse of the initial decoupling matrix, then work out the steady state decoupling matrix G0, make Ki equal to the inverse of that, and that sets up our controller with these structures here. And we've got these parameters here, then we can use as like PID or PI tuning parameters, like in a normal sense. So all our normal rules for tuning, those still apply. And then this controller then is implemented in MATLAB, and one of the ways to implement it is using the MATLAB function block, where again those same parameters are put into the function block, and then they're implemented as a simple little equation here. This is a matrix equation here, so that equation there is essentially the same as this one here. So there is a interesting little example of a multivariable control system design problem, and where you've designed a decoupling matrix using the concepts of initial decoupling and steady state decoupling to come up with a multivariable PI decoupling controller. So hope you enjoyed that, and at that stage we've now concluded the course, and you can now take a deep breath of relief and say, I've now completed the course. I can now concentrate on understanding it fully and preparing for the exams. So hopefully I'll see you when I see you in the Blackboard Collaborate rooms. So thanks for listening, and I hope you enjoyed it.